Hello everyone and welcome back to my channel. Here in this video I'm going to talk about finding a minimum spanning tree of a weighted undirected graph. For this video I'm going to use the Prim's algorithm. You can watch my other video that is about using the Kruskal or the Kruskal algorithm for finding minimum spanning tree in a graph, again undirected and weighted. So both Prim's and the Kruskal algorithm are greedy algorithms. So I'm going to explain how these algorithm works. Especially here, I'm going to talk about Prim's. And here's an example of a graph, graph G with six nodes or six vertices and some edges or arcs. Here we need some like information before we actually, or the way that before we start the Prim's algorithm. We're going to define two like the arrays, one to keep the cost associated with each node for the spanning tree, and at first we put all the cost to infinity. As you see here, I'm going to just put the number 1 here. Each cost of each node is equal to infinity, and then also we're going to put the adjacent node of each node to be also none. So that means that we have not created or we're dealing with an empty set or the empty tree. So also we're gonna start with the with the set T, which is as first as it says going to be empty. So that means we have A. Here I have B, F, C, D, and also H. So these are the nodes that we have, and the T is a set which will contain the edges. And at first it is empty, so we have all the 6 vertices here. So we're assuming that these nodes all can be connected to each other, or in other words, we can create a tree which contains all the nodes. And for sure, in a spanning tree, as we all might know, that the number of edges is exactly the number of nodes or vertices minus 1. So in other words, so I'm going to write here again, the number of edges will be equal to the number of vertices minus 1, as we'll see in the Prim's algorithm. So let's see how it works. In the Prim's algorithm, which is a greedy algorithm, we're going to start with any node that we want. It doesn't matter because at the end, we just need to include any node in the spanning tree. So it doesn't matter which node to start. It's up to us. Here, I'm just going to start with the node A, because it's just based on the order of alphabet. So I'm going to start with the letter or with the node A. And for that node, I'm going to put the cost of the node A to be 0. And the reason that I'm going to do that is because I'm going to just start or the way that is the Prim's algorithm work. It's going to work with the node that has the minimum cost. And as you see, all the nodes or every other node except the node A has a cost of infinity. However, the cost of the node or vertex A is 0, so I can start with that one. So let me then put infinity for all the nodes except the node A, which is my start point. So now we have the like the 0. So for every edge or for every vertex that is connected to the node A, I'm going to calculate the new cost associated, or based on the node A. So here, as at first we see that the cost for C and B and H, which are the neighbors of A, is infinity, which means that the cost associated, or the cost that needs to be spent in order to go from A to C, or just to visit the node C or B or H. So now we see that the cost associated with A is 0. So if we take only, or we spend only 5, whatever is the unit, we can go to the node C. So here 0 plus 5, or just from not 0, but the cost is 5, so it's going to be 5 for the node C. And here change the color. So here also for the H, the cost will be equal to 1, and now the cost for the B also, not that one, but here also will be 7. So the cost from going from A to B will be 7, from A to H is now 1, and from A to C is also equal to 5. Here we're not adding the cost because it's just a spanning tree and it's not a path, and we just want to make sure that all nodes somehow are connected to each other. So what I'm gonna do for every neighbor, and that's again that has the Prim's algorithm works, starting from the node which has the minimum cost, and at first we start with one random node which was A here. Then we are comparing or checking all the neighbors of that node, and if the cost associated with each node is is larger than the cost going from that node, then we're updating the cost. So here I'm going to update the cost for C. Let me change the color. So the cost for C will be equal to 5. The cost for B will be equal to 7, and the cost for H also will be equal to 1. And now that I found that the cost for C, B, and H actually can be smaller, I also can update the adjacent node for C, B, and H as well. That means that which node was the one that I can connect to, and it gives me the smaller cost, which is the node A. So adjacent node of the B will be equal to the node A. The adjacent node of C also will be A, and also the adjacent node of H as well gonna be A. So that's the changes that we have made so far, and as you see, we have not changed the S and T yet. After this iteration, so we're gonna remove the node A from the list of S when S is the set of the node that has not been added to the list or to the like the tree yet, and the T is also, again, as I said, the list of edges or set of edges in the spanning tree. So far is empty. Now we're done with A. So A, we're done, and the very next node in the graph which has the minimum cost, as you see, is the node H. So the cost of C is 5, the cost of B is 7, the cost of H is 1, and cost of D and F both is infinity. So we're gonna choose the node H. As you see here, that's the greedy part, that again, choose the node which has the smallest cost. So by choosing the node H, what's gonna happen, we're gonna look at the adjacent node of that node, which is A, and we're gonna add that pair of like the node as the edge to the spanning tree. So we're gonna add A, and then the adjacent of H, which is A to the spanning tree. So that's what's going to happen. Here I'm going to draw this connection from A to H with the cost of 1. So we added this to the our tree, and so what I'm going to do, I'm going to update the spanning tree T, and it's going to contain the edge A and H. So far, that's what's going to happen. And then the set S will be V minus A so far. That's what the changes that we have made. Now we're going to repeat the process, this time for the node H. The only neighbors that we have here for the H, which is not part of the S, is the node D. So we're going to see if we can update the cost of D or not as well. So the cost of D so far is infinity. However, if we take the edge from H to D, the cost of D will be equal to 4. So what I'm going to do, I'm going to update the cost for D and make it 4, because that's how much it takes to go from H to D. Also, I need to do, so that was the first iteration that we had, and now let's go to the second iteration, which is updating the cost of D to be 4, and also set the adjacent node of D to be the node H. And then also we are done with the node H as well. So here we're going to see what is the next, like the minimum node in the spanning tree, and for sure we are not considering the node A and H anymore. So here I need to update. A and H are not part of S anymore. And now what we're going to see, what is the like the minimum node. So being minimum, like you see here, D is the cost of 4, and then we have the B with cost of 7, C is the cost of 5, and F is still infinity. So between all of these nodes, we have the node D, which has the minimum cost. So in the third iteration, we're gonna see that what we can do. So the D itself was connected to H, so we're gonna add the DH to this here with the cost of 4. So we added the D and the adjacent, which was H, here to the spanning tree that we had. So we so far added 2 edges to the spanning tree. So the third iteration, we expect to add another like the edge at the end of this iteration. So the neighbors of D which are not visited or checked yet are the F and the node C. So let's see. For the node C, the minimum cost so far is 5, which was if it was connected through through the other nodes through the node A with a cost of 5. However, if we go from D to C, the cost will be 6. So it's not getting better, so we're not gonna change the cost of C and also the adjacent of the node C, and A still is better. Now let's take a look at the node F. The cost of F so far is infinity, and that makes sense because as you see here, it's not connected to any other nodes. The cost is infinity. However, if we take the node D to F, the cost will be 8, so that means that we need to update that one to 8. So here I'm going to update this infinity to be 8, and also here I'm going to update the cost for C. So also I'm going to write here no update for C, for the node C. However, we're going to update the node F. So the cost of F will be equal to 8, and also adjacent node of F as well so far is going to be the node D, and also we're done with the node D. Now let's take a look at the graph and see that which node now has the smallest cost. So we are done with H, D, and A. So between C, F, and B, we see that the node C with the cost of 5 is minimum. So we're gonna look at the node C, and we're gonna add it adjacent, which is A, to the tree. So here we have CA added, because as you see here, the adjacent node of C was A. With the cost of 5, we added here. Now we're going to see the neighbors of C, which are F, A, and D. However, we are done with the nodes D and A. So here also let me add this one to the remove it. Also, I forgot to actually add these edges to the tree that we have here. So it was H and D, and then also we had, or let me put it this way because that was actually, yeah, that was H and D, that was correct. And then the other one, which was A and C. So we added these edges so far to the spanning tree, and we removed the nodes A, H, and D from the set of vertices S. So going and choosing the node C. So here we're choosing the node C. It was not bad actually maybe to write the name of things. So choose H. Here we choose D. Here we choose the node A, and now after this one we're going to choose the node C with the cost of 5, and the only neighbors is F. So here, so choose C. What's going to happen here, because the cost of from C to B is 2, which is smaller than 8 that we found from D to F. And we're going to update the cost for F to 2. So cost of f will be equal to 2, and also we need to update the adjacent node of f, which gonna be the node C. So here we're done also with the node C, and as you see we also added that one, and also let me just have these changes here with this gonna be 2. Between the node F and B, now F has the smallest cost, and we're gonna add the F when adjacent, which is C, to the graph. So we're gonna add the CF with the cost of 2, and that means here also need to update the set S and also the set T. So here is going to be C and F with the cost of 2, and again here I'm going to just remove the C from the node S. So far as you see, I have added 4 edges, and that means that it's going to be the last iteration because I only need to add only one more like the edge to the spanning tree. So after this one we're going to the 5th iteration, and we're going to choose the edge which has the smallest cost. So between the node F, as we said, between F and B we have the node F, so we're going to write, so I'm going to here choose node F, so 5, and then here is the cost of the neighbor of F, which is B, which is 9, and as I see there is no way to update it because the cost of B is already 7 and the cost of F to B is 9, so there shouldn't be any update. So let me just erase this one, and we're going to say there is no update. So no update for the node B because it already has the smallest cost. So what's going to happen, we're done with the node F, and here I'm going to remove it from the S, and the next node will be the node like the B, which has the adjacent node of, as you see, A here. So I'm going to add the edge AB to the tree with the cost of 7, and that's going to be our minimum spanning tree. So as you see here, here maybe that was the the choose F, and at the end was the choose B, but again there was no other like the edge any other vertex remain. So that means we're done. And here let me also fix the or add this one to the set T, which is like the A and B. So here all the like the vertices, and then at the end here also here we're going to add the node B, and as you see it is already means that we are done, and the set S is also empty. So just to summarize what we have done for the Prim's algorithm to finding the minimum spanning tree of a graph which is directed, which is undirected but weighted. So we're starting with one random node, and we're going to put the cost of that node to be 0 and the cost of every other node in the graph to be infinity. So that is because we want to use the greedy algorithm, or the Prim's algorithm is greedy and always chooses the node with the smallest cost. So we start with the node A, we put the cost of A to 0 to that one, and then we updated the cost of all other ones based on the weight of the node A, or the node with the smallest cost, to all of its neighbors. We need to update two like the arrays, one that keeps the cost and the other one keeps the adjacent, or keep track of who is the node that caused to have the smaller cost. Then after that we're just repeating the process, and we're adding the edges one by one based on the node that we're dealing with and its adjacent. So here again, when we had the node H, we chose node H. We found that the adjacent of H is A, so that's why the very first edge that we added was the edge A and H. So that was the one, and then we repeated that process again until there was no more vertex in the set S, and the tree was exactly like this many number of like the edges, which is exactly number of vertices minus 1 in a graph in which that every node is connected. So again, as you you remember, the tree Minimum spanning tree, again, the tree has this feature that it does not have any cycle, and so however all the nodes are connected to each other, and the number of edges, the exact number of vertices, -1. Make sure to watch my other video that explains the Kruskal algorithm to find the minimum spanning tree, which is also a greedy algorithm.